Could I have your attention?
Absolutely.
All right, we're nearing the end of our work with the gas laws. Just got a couple more to cover here. We're going to look at Dalton's law of partial pressure first. The thing to keep in mind here is just using common sense. Okay, Dalton's law of partial pressure simply says this. If you have a container, the pressure in that container is going to be the total, or the total pressure of that container is going to be the partial pressure of every gas that's in there. Okay, that makes sense. If I have oxygen in a container, if I have hydrogen in a container, and if I have helium in a container, then the overall pressure should be the combination of all three of those gases. And that you'd be exactly right to think that. The Dalton's law of partial pressure simply says A plus B plus C is going to give you the total. So however many gases you have in there, the partial pressure should add up to the total pressure. The thing that you need to keep in mind is to always use the same units. Okay, so if I'm going to use kilopascals, then make sure they're all in kilopascals. If I'm going to use atmospheres, make sure they're all in atmospheres. If I'm going to use millimeters of mercury, make sure I convert to millimeters of mercury. Here's an example. There's a container which has oxygen, xenon, and helium in it. Okay, so three different gases. The total pressure is known to be 972 millimeters of mercury. So there's my total pressure. I can go ahead and write that down. P total. The pressure total is 972 millimeters of mercury. Now, since my total pressure is in millimeters of mercury, I probably want to work with millimeters of mercury with all of the other gases. Okay, so let's continue reading and see what values they give to us and what units they give. If the pressure of helium, so there's one of my gases, is 0.458 atmospheres, and the pressure of oxygen, there's the second, is 74.1 kilopascals, what is the pressure of xenon? Okay, and it's asking me what is the pressure in millimeters of mercury. So I need to solve this problem using millimeters of mercury. Not a big deal. So pressure of helium, okay, is 0.458 atmosphere. No big deal. I know that for every 1 atmosphere, I have 760 millimeters of mercury. Again, those values on the back of your formula charts that we gave you, you can refer to those, and you'll need to refer to those throughout this unit. Okay. So now I simply need to do the math here. 0.45 times 760, and that gives me 348 millimeters of mercury. Okay, I haven't changed the value. All I've done is change the unit, because 0.458 atmospheres is the same as 348 millimeters of mercury. All I've done is change the unit. Now, I'm also given the partial pressure of oxygen. But I'm given that in kilopascals. Okay, again, not a big deal. I'm given a value on the back of my formula chart that converts kilopascals to millimeters of mercury. I know that for every 101.3 kilopascals, I have 760 millimeters of mercury. Because remember, 760 millimeters of mercury is the same as 101.3 kilopascals and the same as 1 atmosphere. 74.1 times 760 divided by 101.3 gives me a value of 556 millimeters of mercury. My total is 972. I know the partial pressure of helium, and I know the partial pressure of oxygen, so it's simply going to be helium plus oxygen plus xenon equals the total. Okay, so 972 is the total. This is my X, because that's what I'm looking for, xenon. I know oxygen is 556, and I know helium is 348, sorry. So 348 plus 556 gives me a value of 904. So the value for xenon is going to be the difference between 972 and 904. So X equals 972 minus 904. So the partial pressure of xenon is 68 millimeters of mercury. Again, remember, you can pause these videos at any time. Moving on. So now we have Dalton's law still. Remember, the Dalton's law says that the partial pressures all equal up to the total. Okay, but what if we're taking a sample of gas over water? Well, we've got to take into account what the pressure, the vapor pressure of that water would be. So Dalton's law over water. Remember, P total is going to be whatever the pressure of water is plus the partial pressure of the gas. Okay, so again, it's just a total of the partial pressures that we're looking for. Here's an example. You got 50 milliliters of hydrogen, and it's collected over water. And that collection, or that sample of gas, has a pressure of 850 millimeters of mercury at 27 degrees Celsius. That temperature is important because we're going to have to refer to this chart down here for the temperature based on the vapor pressure based on the temperature. So we want to know, what is the pressure of the dry gas? That simply means, what is the pressure of hydrogen without water being there, without the water pressure being there? Here's how we're going to set that up. Remember, P total equals the pressure of water plus the pressure of the gas. In this case, it is hydrogen. Okay? So I know 850 is my total pressure. The pressure of water at 27 degrees is 26.7 millimeters of mercury. I know it says torr, but that value, okay, notice, is the same as millimeters of mercury. There's the value of water, and I'm looking for the value of X, my unknown, or in this case, hydrogen. Okay, so how do I get X by itself? I'm adding on this side, so I need to do the opposite function, which is subtracting. So 850 minus 26.7 equals the value of hydrogen. In this case, it is 823 millimeters of mercury. That is hydrogen. All right, so pretty straightforward. Dalton's law of partial pressure. All you need to keep in mind is it's a combination of every gas present. If you're taking a sample of gas over water, it will tell you that in the problem. Okay, so you're going to look at over water. That's what you're looking for, and then it'll give you a chart to refer to based on the temperature. All right. Last gas law that we'll look at is the ideal gas law. So this is perfect world scenario. Nothing has affected this gas. This is the ideal gas law. So if a gas behaved exactly like it's supposed to under every or in every circumstance, this is what it would do. Anytime that you have pressure, volume, temperature, and a number of moles that are all changing, this is when you need to use the ideal gas law. Again, we're going to write down everything that's given to us in the problem. Notice in this problem, you're only given one pressure, you're given one volume, you're given one temperature. So there is no initial temperature and final temperature. You're always going to just use one variable for each of those values. Okay? Example calculation. How many moles of oxygen must be put in a 0.5 liter flask at 20 degrees in order for that flask to have a pressure of 1.7 atmospheres? Okay. So what is the initial pressure? Are we given a pressure? No, we're not. That's the thing we're looking for. So pressure is my question mark. Volume, is the volume given to me? Yeah, it's given to me right here, 0.5 liters. And you're told a temperature. The temperature is 20 degrees Celsius. Remember, 20 degrees Celsius, or got to change that to Kelvin, so 293 Kelvin. Okay, so I've got P, which is what I'm looking for. I've got V, I've got T. N is, N is actually what I'm looking for. P is given to me in my problem. 1.7 atmospheres. Okay, you're told that it has a pressure of 1.7 atmosphere. And N is what I'm looking for. So I'm looking for how many moles of gas would I need in order to have that pressure. Sorry about that. So I'm given pressure, given volume, given temperature. I'm looking for N. This value right here, R, is the ideal gas constant. And it is always given to you. Okay, this, again, these values are on the back of your formula chart. If you are dealing with millimeters of mercury, then this is the value you're going to use. If you're dealing with atmospheres as your pressure, then this is the value you're going to use. If you're dealing with kilopascals for your pressure, then the value is the 8.314. So here's how that works. R is always constant. It's always going to be one of these three numbers that you're going to plug in. Okay? Pressure, volume equals nRT. So PV equals nRT. What am I looking for? I'm looking for the number of moles. So how do I get N by itself in this equation? I've got to divide by RT. That will cancel these out on this side. And anything I do to one side, I have to do to the other. So PV over RT equals the number of moles. Awesome. Now all I have to do is plug those values in because I've got them right up here. Okay? So pressure, 1.7 atmosphere. That's important because remember we need the unit for pressure in order to know what value for R we use. My volume, it's always going to be in liters, so 0.5 liters. And I'm going to divide by R and T. So the R value that I'm going to use this time is the 0.0821 because it has atmosphere in its units. And my temperature was 293 Kelvin. Multiply the top, divide by everything on the bottom, and the number of moles that I have to have in order to have that pressure is 0.037 moles. So again, remember the ideal gas law is the law that we'll use and the formula that we'll use if pressure, volume, and temperature are not changing. Nothing's changing there. I only have one value for P, one value for V, one value. What happens though if you're given a problem that starts in grams? Okay? Remember, I've got to use the PV equals nRT. That N is the number of moles. Okay? But remember from our dimensional analysis problems, if we're given grams, our mass, we can get to moles. Remember, the relationship between mass and moles is molar mass. So in this problem, I start with 1.17 grams of helium. That's put into a 500 milliliter container at 10 degrees Celsius. What would be the pressure of that container in millimeters of mercury? So that's the key there. We've got to use millimeters of mercury as my unit for pressure. Okay? So I'm looking for P. I'm given a value for volume, and it's 500 milliliters, or it's 0.5 liters. Remember, there's 1,000 milliliters in a liter, so if I have 500 milliliters, that's half of a liter. Okay, the number of moles, I don't know yet because I'm given mass up here. Okay, the R value that I'm going to use, go back. The R value, and if I'm trying to solve for millimeters of mercury, is this one right here, 62.4. Okay, so we're going to plug that into our formula over here. R is 62.4 liter millimeters of mercury over mole Kelvin. And my temperature is 10 degrees Celsius, or 283 Kelvin. Trying to solve for P. So P equals nRT divided by, so in this case I'm given number of moles. We've got to find number of moles. I start with 1.17 grams of helium. Look on my periodic table. I know that if I had 1 mole of helium, it would contain 4.0 grams. So what is 1.17 divided by 4, it is 0.293. So that's my value for N. So 0.293 times R, which is 62.4, times the temperature, which is 283, all divided by the volume, which is 0.5 liters. So what is the pressure? It is 1.03 times 10 to the 4th millimeters of mercury, or if you want to write it out in longhand or standard form, it's 10,300 millimeters of mercury. There's a problem using the ideal gas law where I'm starting with grams instead of moles. Okay, I've got to do a conversion and then plug the number of moles into that problem. Hopefully this helps you guys and you're able to work through some of those examples. Again, remember, if you have questions, post those on your Google Doc or on your questions to consider boards in your classes.
We're them, we're they. We are the men in black.